Alright, today we're talking about 6.4, the last section of Chapter 6, which is parametric equations. So to kind of start, we want to talk about what is a parametric equation. Well, a lot of times, right, you're given a coordinate point, x and y, which is, from what we know, is just a number, right? You're given the point 3, 2 or 3, 4. But sometimes in real life and in a lot of math problems, they're going to be dependent on a parameter, right? So the x point, in this case, could be dependent on cosine of t. T is just a number or an angle that we plug into cosine, and that determines what my x value is. Same thing for sine. T is just an angle that or a real number in radians in this case, that is an angle that we plug into sine, and it spits out a y value. So we call those values t the parameter, and we call the equations that these make parametric equations, and we'll be focusing on just x and y being dependent on cosine and sine and different trig functions. So we're going to just be rewriting them in the form of an xy equation. So when we say eliminate the parameter of a certain problem, we're going to be talking about that. We only want you to give the new equation in terms of x and y, and then we might say to graph it. So let's try this out. I'm given the two parametric equations, x equals 3 cosine t and y equals 2 sine t. So what I'm going to do is I'm going to start out by writing them in terms of solving it in terms of cosine and sine. So for the first one, I get cosine of t equals x over 3, and I get sine of t is equal to y over 2. Now the reason I do that is we're always going to be using one of our Pythagorean identities. So if you go back to your formula sheet, you're given multiple different Pythagorean identities. We have to choose which one. Well, I have it in terms of cosine and sine, so I'm going to use the one that says, hey, this is cosine squared of t plus sine squared of t equals 1. That's one of my Pythagorean identities. And now I'm going to dump in x over 3 and y over 2 where I see my cosine and sine. So when I do that, I have x over 3 quantity squared plus my y over 2 all squared equals 1. Now we can simplify that down a little bit to be x squared over 9 plus y squared over 4 is equal to 1. Now we're going to have to think back to our maybe algebra class here to figure out what does this thing look like in order to sketch it. Oh, just before we do that, a quick recap. When I say eliminate the parameter, this boxed equation is what I want you to give. You need to give this equation to get full credit. But now in terms of drawing them, graphing them, there's two different types of graphs you're going to be dealing with. We're going to be either dealing with ellipses, which is essentially an oval or a football, or we're going to be dealing with hyperbolas, which we'll get to those in just a second. I think that's the third example. But we need to think back to my algebra class when we dealt with ellipses. And an ellipse is of the form x minus h all over a squared. Oh, sorry, this is x minus h squared plus y minus k quantity squared all over b squared equals 1. Where hk, the point hk, is my center, and then we'll talk about what a and b are. Notice in my boxed equation down here, I'm not subtracting anything from x and y, so my center point, is at 0, 0. Now notice these are a squared and b squared, so for my x value, I'm going to go to the left and the right, a. That's the distance I'm going to go either way. So in my case, for my x value here, it's all over 3 squared. So to my x value, so left and right, I'm going to go 3 either way. 1, 2, 3. Then in my y value here, my second term, it's all over b squared. Well, that's all y squared is over 2 squared. So I'm going to go 2 up and 2 down, or 2 in my y direction both ways. And from there, I just connect the dots. And that's my graph equation of this parametric equation. So let's try another one, maybe a little bit more difficult. Again, I'm going to solve for sine and cosine. So sine of t is equal to x minus 3 cosine of t is equal to y plus 2. And now I'm going to dump them into my Pythagorean identity again. Remember, cosine squared plus sine squared equals 1. So I have, in this case, I'm going to write the sine one first. I have x minus 3 all squared plus y plus 2 quantity squared is equal to 1. Now notice this is technically over 1 over 1. So the distances I'm going in the x and y direction, remember last time we had 3 and 2, this time it's going to be 1 and 1, so it's actually going to be a circle. It's only going to be a radius of 1. But my center is different. Remember back to my equation here, the point xk is my center. Remember, I'm subtracting h and I'm subtracting k, so the signs are going to be opposite of what we would think. So my center in this case is going to be, well, x minus 3, x minus h, so my center is 3. Since I'm adding 2 here, it's going to be a negative 2. So my center is at 3, negative 2. So 1, 2, 3, 1, 2. My center is right there. Remember I said earlier, since we're dividing it by 1, 1 squared, technically if we want to think of it in those terms, so I'm going in the x and the y direction 1 each time. 1, 1, 1. And then again, I just connect the dots. And I have a little circle there. And that's my graph of my parametric equation. In order to get full credit, you would have to give me this boxed equation here. That is eliminating the parameter. And then for the last one, the hardest one, I have secants and tangents. Well, I'm not going to do anything differently right now other than solve. I'm just going to solve for my trig equation here. So in the first case, I have secant of t is equal to, I would subtract 3, divide by 2, so I get x minus 3 over 2. And I have tangent of t, subtract 2, divide by 4, I get y minus 2 all over 4. Now the question is, what identity, what Pythagorean identity am I going to use? Well, if you go back to your formula sheet, you have the identity tangent squared of t plus 1 is equal to secant squared of t. I'm going to get both of my trig functions on the same side, so I have 1 is equal to secant squared of t minus tangent squared of t. And then all of a sudden, hey, I have secant t, I have tangent of t. So I'm just going to dump those into my formula. I'm going to write the 1 on the right-hand side of my equation just to keep it consistent, but I have x minus 3 all over 2 squared minus tangent of t, I almost wrote tangent there, squared minus, I have y minus 2 all over 4 squared equals 1. Notice the difference here is I have a minus sign in between my terms instead of a plus. This minus sign makes it a hyperbola, excuse me. We'll talk about how to make those hyperbolas, give a bit of a crash course. Well, let's see where my center is. My center is 3, 2. So I'm going to write that as 1, 2, 3, 1, 2. Now, how many in each direction am I going? Well, for the x direction, I'm going 2 squared. So my denominator is 2 squared. So I'm going 2 in the x direction. So 1 point there, 1 point there. For the y direction, my denominator is 4 squared. So I'm going in the y direction 4. So 1, 2, 3, 4. 1, 2, 3, 4. Just like making my ellipse. I saw, hey, 2 squareds in my denominator, so I'm going 2 in each direction along the x. And then for y, I'm 4 squareds in my denominator, so I'm going 4 up and 4 down. The only difference now is with my hyperbola, I'm going to make a box out of these. The reason I make that box is because my diagonals here, the diagonals of my box, give me my asymptotes of my hyperbola. So it's either going to go up and down, or it's going to be going left and right along my asymptotes. How do I determine which one it is, though? Well, I look at which one's first in my equation. The x value comes first, right? Order matters in subtraction, so either the x has to be first or the y has to be first. In this case, my x is first, so I'm going to be opening up in the x direction. So I start at the point that's on my box that I wrote, and I follow my asymptotes, going to the left and to the right. And that purple curve is my answer. That's the graph of this function right here. So remember, just as a bit of a recap, I know this was kind of a crash course in ellipses and hyperbolas, but for eliminating the parameter, you have to give me this equation. When I say eliminate the parameter, I want an equation of x and y. Usually it's going to look something very close to what I've written here. Secondly, for graphing the equation, you have to see, hey, is this a plus or a minus in between the x and the y terms? If it's a plus, it's an ellipse, a football. If it's a minus, it's a hyperbola. And if you have any more questions on how to graph hyperbolas, we can go over a few examples in class. But go ahead and look at your assignment down here. Maybe try a few examples before class if this is a bit confusing, and then write your summary and any questions you might have.